Day. Please welcome to the stage Yoav Weiss.
Hi, thanks everyone. Can you, just a second? The font, can you increase the font? Yeah, so hi everyone. So my talk today is about the challenges with trust assumptions in interop protocols, cross L2 protocols, and then to show how EIL address these challenges. So one question we need to ask ourselves whenever we use an interop protocol or anything else on the blockchain is who do we have to trust and how much? Who could hurt us and what could they actually do to us? So one problem you have to think about when using, for example, intent protocols or anything that involves moving state from one chain to another is who will testify that the operation actually happened at the destination? Because the destination, there is no direct communication, at least not fast one, between the destination and the source. So let's say you went to a solver and asked it to do something, and it does it or it doesn't do it at the destination. But now the solver wants to claim the funds at the source, at the source chain. So someone needs to testify that someone need to attest on L1 that it's okay to release the funds back to the to release the user's funds to the solver because it has been fulfilled. So now the question is, who is authorized to attest for it, and what happens if they lie, if they submit a false attestation, or if they just stop working? So in some protocols, it's a permissioned oracle, which brings some trust assumptions, of course, because you can't easily replace it. There are other protocols that protect it using a dispute mechanism, and then you have to ask yourself, who do you trust for the dispute mechanism? Who you are appealing to someone. When you appeal, who are you appealing to, and could they collude with a malicious oracle? Now, another thing we need to consider when using the blockchain is censorship resistance and execution liveness, because that's what the blockchain is about. So in many protocols, the user funds become associated, are tied to a specific solver before the operation takes place at the destination. And this is important for efficiency. It's much harder to do a protocol, to implement a protocol without it. But then the question is, what if it doesn't execute? Could the user easily switch to another solver or relayer, or is the user stuck for a while? And in some protocols, you actually do get stuck. You actually do get stuck. You send the fund to someone, and if they don't deliver, then you are stuck at least for a while. In other protocols that are in better implemented protocols, they have something like, for example, having an exclusivity period for one solver. But if the solver doesn't take advantage of it, then after a while, any other solver can also do it. So that's already better. But there is still some time in which your funds are associated with someone, and this someone can now delay you. Another issue is that the solver could grief you. So since the solver is executing on your behalf, so you're basically using an intermediary to run to execute your transaction at the destination, They could mess with your execution because this is not a transaction, it's a call inside a transaction. So some things that can do is, for example, making your call revert unexpectedly or misbehave and do something that you did not intend, and it's still considered, the intent will still be considered fulfilled. So it's like one example, one easy example is to make your call at the destination with insufficient gas. Suppose you have a relayer. Now the relayer makes the call with insufficient gas, so you run out of gas inside your call, but they do have sufficient gas in the outer call to emit the fulfilled event. So now it's considered. So now the intent is considered fulfilled as far as and an oracle will attest that it was fulfilled even though the inner call actually reverted. So you end up having funds at the destination, but without your call getting executed. Another such example that is more, because I mean the gas thing could be mitigated. Unfortunately, currently many protocols don't pass a gas limit, but you could implement a protocol with a gas limit that the user signs as part of the intent and say, if I'm not given this amount of gas, then it's not considered fulfilled. But there are other ways there are other attacks that are easier, that are harder to mitigate. For example, you could wrap it, since it's a call, you can wrap it with an outer call. So what if the solver calls you, for example, through a flash loan? Suppose you have the solver takes a flash loan for a very large amount, and now it can move token prices. And then it makes your DeFi call at the destination, and the DeFi call fails because they move the price using a flash loan. After it reverts, after your call to a DeFi contract reverts, they just repay after the intent is considered fulfilled, but without your intended result, they can still repay the flash loan. So this is another example of being able to mess with the state at the destination. There are other subtle examples, like for example, many protocols implement reentrancy protection using reentrancy guard. So what if you are going to use, so your intent is going to use something that has reentrancy protection, but the solver also calls, so the solver calls this protocol with reentrancy protection, and from its callback, it now makes a call to the intent protocol to fulfill your intent. So now your intent gets executed, it reverts on the reentrancy guard, but it's still considered fulfilled because they made the call for you, and then they exit. So all of these examples bring us to a place where the user pays the fee, the solver got the fee, but the user did not get the intent executed. And you can think about it not just as griefing, because it's also a very strong form of censorship. Because now another solver can't help you. Let's say when looking at a protocol that implements exclusivity period, suppose the exclusive relayer or solver, so the one that got exclusivity decides to do this to you. So now now the intent was fulfilled during the exclusivity period as far as the protocol concerns, even though they reverted your call. And now, after the exclusivity period, it doesn't matter. Nobody can help you anymore because the intent, it no longer exists. It was fulfilled. So this is a strong kind of censorship that is quite hard to fix. Another question now is, so we talked about what could happen to the user. Now let's see what could happen to the solver. I mean, especially if we try to decentralize solvers, which I think we should, then who could hurt the solver? And one example we already discussed. This is what happens if the oracle refuses to attest. So since the solver depends on an oracle attesting for the fulfillment in order to get paid. So what if it doesn't and it's a permissioned oracle? So that's a simple example. But now we have to ask ourselves also, in a decentralized and permissionless network, could users also mess with solvers? And in many cases they can. So suppose we want to have a decentralized solver network that behaves much like a mempool, just like the transaction mempool. Now we need to consider denial of service attacks on this network. So it's really hard to create a mempool for intents. It's really hard to create a mempool because the intent can be quite intensive to simulate, and you can easily flood such a mempool with a large number of intents that seem fulfillable. Like when you simulate it, it seems fulfillable, but actually it's going to fail on chain. And you could do something, for example, like send operations that take a lot of computing power and then check the time. Like after spending all the compute power, they check the time and they fail after a certain time. So like when you simulate them initially, when you see it entering the mempool, you can say, okay, it looks fine. And then so every solver checks it and sees that it seems fine. But then when they actually want to submit it at a destination, it no longer works because the time has changed. Or they could just check the slot of a frequency changing slot, such as the price feed for the price feed or the Uniswap price of some high velocity token. So now all the solvers spend a lot of resources and they don't get paid for it, which can create a load on the network. And therefore, such networks tend to become centralized or to limit or protect themselves by limiting to specific uses that are known to be safe, instead of having a generalized intent framework. Now, an even stronger form of this is griefing the solver by causing it to revert on chain. So what happens if the user sends intents that they look fulfillable, and even when you simulate them at the destination, simulate them against the current state of the destination, they still seem fine. But then when you put them on chain, they revert. For example, if they do a time check, or they check this like frequently changing slot that changes during the block, then if you simulate it against the end state of the last block, but then the intent happens not to be the first transaction in the next block, then it would revert. But now the solver actually pays for it. The solver paid gas. So which brings us to a trade-off that and there is no good trade-off here. So there are two options. You could charge the user even though the intent reverted and was not fulfilled. But then it means that the solver can grief the user, just like we described earlier. You could cause the intent to be executed in a bad way, and the user still pays for it. Or the other option is you say you don't charge the user. But if you don't charge the user, then now the user can grief the solver. Now the solver pays for these reverts which the user causes, and the user can cause a large number of those. Now let's take a look at how EIL works, and we'll see why these problems don't exist there. So this is the basic flow in EIL. Let's say Alice. So Alice wants to mint an NFT on chain B. It costs 1 ETH. She doesn't have any ETH on chain B, but she has enough on chain A. So she prepares 2 user ops signed by a single signature, because we have a multi-chain account that allows you to use one signature for multiple operations, different chains. So the first user op runs on she sends the first user op to chain A, and it locks 1 ETH plus whatever fee she is paying. It locks it for a very short time on chain A. And now we have XLPs. These are the entities that provide the liquidity and the gas at the destination. So the XLPs compete on sending her a voucher, which she's basically buying a voucher that she's going to use on the destination chain. So they get this. They compete on providing the voucher, and it's actually on a competitive environment. It's going to happen within the same block because she submitted it to the mempool, and since they compete against each other, then an XLP sees that it can claim the fee right now in this block, so it makes sense for it to include the voucher together, like to bundle it with the request, which means that the user now gets, so Alice gets a voucher immediately in like 0 latency. And as soon as it lands at the source chain, she can immediately use the voucher. Now, how does she use the voucher? She now appends it to, the voucher is a signed message from the XLP that gives her the funds. It's an atomic swap. So basically, to claim her funds, there was this voucher, and this voucher can now be used to claim funds from the balance of the XLP. She appends this to the user op she prepared for minting the NFT, and she puts this. She submits it to the destination chain, to chain B herself. She doesn't use an intermediary. She just sends this to the destination. Now it uses, so this user op uses a paymaster contract, we call it a cross-chain paymaster. This paymaster verifies the voucher, it pays for the gas, and it gives her the 1 ETH liquidity that she asked for. And this is deducted from the XLP's balance in the paymaster. And the operation gets executed. So a call gets executed, the NFT is minted. And then after a dispute period, the XLP gets the funds on gets Alice's funds on chain A. So that's how EIL works. Now let's see how it. Why does it solve all of these problems? So we moved most of the logic to the wallet. This is an account. It's an account-centric or a wallet-centric interop, which means instead of having a solver, you run all the logic locally. Now, since the user self-executes on every chain with no intermediaries and using this single signature, which gives you great UX, many of the risks become irrelevant. The XLPs, they give you a voucher for gas and tokens, but they don't execute anything at the destination. Actually, there is no transaction by the XLP at the destination, and they do not communicate directly with the user. It's everything happens on-chain at the source chain. Now, the voucher is also atomic, behaving similarly to HTLC. So there is no mid-state in which the user sent the funds to an XLP and doesn't get the funds on chain at the destination chain. So there is no oracle because we don't need one. We don't need someone to attest for correct execution at the destination because the user executes at the destination. So unless Alice wants to screw up her own transaction, you don't need to prove anything about it. Now, one thing that could happen, an XLP could try to withdraw the funds, to provide a voucher and concurrently withdraw the funds at the destination, so now the voucher cannot be used. Now, in this case, this is a provable offense. You can, so Alice or any of the other XLPs, and anyone actually, could prove this at the destination because everyone sees the voucher that was given at the source chain, and they can now make a call to a prove function at the destination, and the paymaster sees, yeah, this voucher is valid and it's insolvent, meaning that this is slashable offense. So this sends a message to L1, and every XLP is staked on L1. So this XLP is getting slashed, and whoever reported it gets compensated from the stake. So the incentives are built in a way that Alice's funds don't get delayed because the XLP gets part of the stake for reporting, and it gets another part of the stake if it provided an alternate voucher. So from Alice's perspective, if the voucher was insolvent, then in the next block, it's likely that she'll receive a voucher from another XLP. And from her perspective, nothing happened. There was like a 1 block delay. She still has a voucher that she can use. And the incentives there are, first of all, the alt voucher now gets the fees. So like the signer of the alt voucher gets the fees instead of the original one. And in addition, it also gets a part of the stake. So you get an extra kickback for delivering this. And then later, when it gets proven on L1, this XLP gets the stake of the first XLP, and it gets the funds released to it. So the only dependency here is on canonical bridges, which every rollup has. There is no, instead of an oracle, you can just freeze the funds and handle the dispute through layer 1. Now, there's also no censorship vector because the user self-executes the operations, so there's no one's supposed to execute on your behalf, and therefore no one can censor you. The competition between the XLPs incentivize that you'll get the voucher since they are permissionless. So if one XLP doesn't want to give you a voucher, then someone else will. And they don't even know what you're going to do since you don't show them your call. They don't know that Alice is going to mint an NFT on another chain. They only know the amount. They only know the amount and the destination chain. And they compete on who gets the fee. So, and they cannot, and once they give a voucher, the transaction is over for them. It's atomic. So now they cannot interfere in any way. They cannot somehow make it fail for Alice because she's the one using the voucher to execute her call. The griefing vectors that we talked about, like sabotaging the execution, also can't happen because Alice self-executes. So she's not going to wrap her own call with a flash loan that's going to get her reverted because she wants it to succeed. The operation always runs exactly the way that the user intended. And it's also easy in EIL to make the XLPs decentralized, make it everything permission and decentralized because we don't have all of these those vectors against it. So the XLP cannot be dosed by bad intents because you don't ask it to execute something, so there is no call that might revert to the destination. The XLP doesn't handle calls. It just takes your funds, gives you a voucher, which is the same operation. And therefore, it doesn't need to spend any execution resources. It doesn't need to simulate anything. All it needs to, it sees that you lock the funds, and it gives you a voucher in order to receive these funds. Since it cannot fail, so this operation cannot fail, you can't give a voucher and not get paid, then we don't need to worry about denial of service. And it cannot be griefed at the destination using reverts because, again, it doesn't care about execution. Whether Alice reverts at the destination or not, they don't care. They get paid the fee either way. So the problem of executing something on users' behalf is a really hard problem. That's something that we've been thinking about in a while. EIL solves it by not having someone execute on behalf of the user, which removes all of these problems. Now, so the user self-executes. The XLP just compiles the fund, provides the funds. We don't need oracles. We don't have the censorship problem. No need to worry about reverts. So it's easy to decentralize, and the settlement is atomic. And in addition, you get the great UX of a single signature and the lowest latency possible because of the mempool incentives. So this makes EIL both great UX and trust minimized. And it works because the user is always under full control. The user has full sovereignty over the execution at all times, and interop becomes trustless. I'd like to take the opportunity here to invite wallet developers and dApp developers. So please talk to us if you want to explore integrations. We launched a testnet, and we're going to have some at the hackathon at Global. We're going to have some prizes for building on EIL. So please talk to us. All right. Thank you.